So let's say you're given a large graph, okay, so one that is not trivial for you to just look at the list of vertices and the edges as sort of a table and get anything out of it. And you're told, let's find what's interesting about it, right? So if you look at the literature, there's usually two ways in which people can draw these large graphs. One of them is known as a matrix diagram, in which what you do is you lay out your list of vertices, and it becomes sort of like a matrix, and then you draw it when there's an edge between them. And in here, this problem is essentially how do you permute these guys so that you get some interesting structure out of there. And the other way to draw a graph is called a network diagram, which is sort of what you'd think of it as sort of like a node and link drawing, in which the problem really is where are you going to put each of these guys there so that there's in some sense some larger structure that comes out there. Today I'm going to be talking about network diagrams for a couple of reasons. One of them is that I think that a lot of graph problems, when you start to think about how do you want to draw them, it makes a lot more sense to use network diagrams instead of matrix diagrams. And in particular, what I'm going to be using today is really sort of tailored for network diagrams, and I'm going to tell you soon what it is. But there's an interesting reason why I don't think matrix diagrams are the ideal way to look at a graph, which is, in a sense, what you're looking at is not your graph, it's more of what happened with that particular permutation and what is the effect in here. So all of them look really nice in a sense, but they look really nice regardless of the order. So it's hard to tell whether something that you got there is good or not. So for example, there, I'm just sorting that with the names of the characters of Les Miserables. Okay, so now you have two characters interact with each other in the play. There's a link between them, right? And you look at that, it's like, is this good? Is this not good? So when you do some sort of clustering algorithm, and then you say, okay, clearly this is better. And so in a sense, I would say that these, on the face of it, they look really nice. And they look equally as nice. When you see this one, you say, ha, yes, that's obviously, there's structure here, and now you can see they are colored with respect to the chapters in which they're in. And so obviously you can see that the clustering did something sensible there, right? And if I change to frequency, there's something else there, right? But the interesting thing is that I had to pick some other criteria to sort them, to try them out, and to see what happened there. Right, so I'm taking the graph and then I'm doing something else with the graph that's not necessarily to do with the structure of the graph itself, right? The clustering is taking the structure of the graph, and so it's not clear whether you're visualizing the graph or the results of the permutation. And in our heads, it's much harder to think about what happens with the permutation. It's sort of more complicated structure than it is to take and decide each vertex independently, where does this go, right? The problem on a network diagram is, where am I going to place this one vertex, right? And this decision is, in a sense, much more independent than the other one. Then what happens if I shuffle this other guy here, right? It's going to move all the other guys a little bit to the other side, and so it's a little bit more indirect, right? And so in this sense, I like network diagrams because they are much more direct, right? I draw this, and as you're going to see, a lot of them are going to end up looking like hairballs, which, if you've heard the term, sort of like this ugly mess, and then we know, okay, this particular drawing didn't succeed. But I think it's a little bit more direct. So this is where I'm going to stay most or all of my talk today. So the state of the art for drawing network diagrams is essentially a physical simulation idea. So what you do is you think of your graph, and each vertex of your graph is going to be a positive charge. And so positive charges repel each other and have this fall-off law, right? And so you just say, okay, I'm going to put them in. For each edge on the graph, I'm going to say there is a ideal spring there that says some length. Let's say all of them have unit lengths. And this has some system, you can sort of just put it there and let it dissipate the energy, right? And so essentially all you say is, okay, edges are springs, vertices are point electrical charges, the final layout is whatever is given by your energy minimizer. And nowadays, if you use things like these multipole methods for doing the energy minimization, you can actually get this to scale pretty well, right? So use the same kinds of codes that people do for gravity simulations instead of charge, but it's the same idea. And you can run things with like hundreds of millions of vertices overnight on a big machine, and it works. Yeah?
Usually, how many edges do you have?
They're usually much sparser.
Okay.
So the edges here, so I think, so this is actually, I can tell you, it's a good thing you asked. So as before, so can you see this? Okay, so it's a little bit messy too, right? And it doesn't get everything as it perhaps you'd expect. In particular, I already told you this is a complete binary tree. So you'd expect this nice, perfectly distributed sort of radially around it. And it doesn't get that because we're running an approximate version of this algorithm, and I'm going to talk about that. But it does elucidate something that you'd expect, which is a binary tree kind of partitions things, right? So you can see this gross partition of the space around here, and I would argue that in here you simply don't see that. Okay? So it's hard to tell, okay, what are the partitions here, and you don't see it. And perhaps you don't see it perfectly that this is, perfectly recursive, but it gives you a better global notion of what this is, in my opinion. So
what stops you from getting a nice radially symmetric?
It is the approximation that we're...
The other one.
On this one, simply the fact that you're not asking for it on the algorithm, right? That the total energy of that system in which things are rated might be larger than one which it isn't, and all it's trying to do is separate vertices locally, right? So it's just that we didn't ask for the algorithm to do it, we shouldn't expect it to do otherwise, right? Soren's shaking his head.
Yeah, I think it's a local minimum problem of the mass spectrum.
Perhaps it's a local minimum problem as well.
Because with a binary tree, and if you have, and you really do, and well, I mean that's the other problem.
So the reason I don't believe that's the case is that this algorithm is actually multi-scale. It does graph coarsening, and so it will coarsen it to as little as it can. It will lay those out, and then we'll do it recursively, and you still end up with something like this. So it might be that the coarsening and the separation rules are not like that, but I don't think it's that simple. Okay, the energy minimizer simply is not trying to, if there is no edges between any pair of vertices, it's not trying to do anything besides keeping them minimally separated. But with only a square law, right? So two things that are at distance 5 from each other, repel them as well or as little as two that are at distance 10 from each other.
You keep going. It should, I mean, if you do just 10 like...
But that's what this thing is going to do.
Yeah.
So this thing is called that it's a little stupid name, but it's essentially it's transmodularization via approximate low rank SVD, and this is what we're going to talk about. So the first thing is, what is transmodularization, okay? So we're going to turn the problem a little bit around, and we're going to say instead of trying to do this spring electrical physical simulation thing, we're just straight going to ask to directly match the metric that we get. Because we know that a lot of graphs have good metrics, and we're going to say, well, we can place vertices, right? So we can take X as being the placement of vertex I in our ND space in case R equals 2, and we can say they have a distance between them. I can have a graph metric 2, and I can measure the distortion as a square loss. And I can say, let's put some weights in them, okay? And in this talk, we're going to consider that the weighting function of this guy is just the inverse of the graph metric of those, okay? So the further out they go, the less they should influence each other. People have run tons of user studies on those, and these tend to be the good choice. And for us, it will turn out to be critical that we use this one, and we'll see why later on. How do we solve this? Just take the gradient with respect to xi, and then you'll get something like this, okay? Don't worry about much of the details. Essentially, you just rewrite it a little bit, and it gives this, okay? And now, if you've seen the sort of expression in which you have the sum of the differences between here, so you have differences with a term in this, and difference with a term there, this should look to you familiar. This is how you get a Laplacian matrix out of that, right? And so here we have one Laplacian matrix with these terms should equal one Laplacian term with the other terms. So if you find a layout that satisfies this, this is a minimum of your embedding, and this is a good one, okay? And we're just going to fix point this. We're going to start with a guess, and we're going to use that guess to get to the next one. We're going to do this over and over and over and over again, okay? And when we find that, this is our final result, all right? So again, so the Laplacian matrices, if you haven't seen them, so this is what LW would look like, is the weights of these terms, right? So these are the Wij's. On the diagonal, you get the negative sum of the other guys, because you're accumulating the sum, right, over all of them on xi, right? And on ij, you get each of the individual terms, okay? And so essentially, your matrix looks like a diagonal with all the sums and a bunch of terms those, right? And it's the same thing for the other term. So all we have to do is compute these over and over again, and that's your recipe. So you're done, right? Well, there's a few snags with that. The first one is, this is not zero everywhere. And I just told you that these are tens or hundreds of thousands of vertices, right? So if it's 100,000 vertices, you can't even fit this in memory on a largish machine, right? So you're sort of dead on arrival. So how do you do that? Right? The other problem is, then you have to invert that. It's cubic time, right? So you sort of need cubic time and quadratic space for this version. If you can get away with that, this is actually the state of the art in graph drawing. It looks really great, okay? So if you can put a graph metric, this is actually what it should do, all right? But now start thinking about this, and you kind of look at this expression, and both of these guys are dense, But really, the equality is on when you multiply this down by something that's v by d, which is a much lower version. And d in our case is 2. Okay? So your equality really is kind of throwing away a lot of the stuff that happens here, because you're in the end sort of multiplying it down and projecting it down to 2, right? So maybe we don't need all that stuff there, right? Maybe we can find versions of that work just as well, but are lower dimensionality. And this is what we're going to do. Okay? So let me just give you some intuition as to why this should possibly work. And the reason is simple. So the first thing is, let's stop thinking about graphs for a while, and let's just say I gave you endpoints that live in d-dimensional space, okay? And then I tell you, give me a matrix in which each entry of the matrix is the squared distance. So you take the distance of each 2 elements in RD, and you put the squared of the distance of that, right? And I tell you, now, if you give me that matrix, the rank of that matrix has got nothing to do with n. It is actually bounded by the dimensionality of the space in which you're living in, okay? So if you put your points in R2, it doesn't matter how many points you have. The total rank of that matrix is 4. Okay, you might have 1,000,000 points. If you measure the distance, square distance between them, it doesn't matter how large your matrix is. You can actually represent that with a tall matrix that's n by 4 and a fat matrix that's 4 by n. And you can get that exactly embedding with error 0. Okay, so you don't need n square elements if you were exactly in this case. All you need is n times 4, and you get exactly the same matrix. So this is sort of encouraging, right? It's telling us that exactly what our intuition is saying is that if your things sort of live in a low dimension space, maybe there's something you can do and you can represent that a little bit better. So this is the trick that we're going to do. Okay? And the proof of this is really trivial. You just expand out the inner products and the square distances and you get that automatically. Okay? So there's no magic there. Like, this is really just arithmetic. You just prove it with your hands pretty much. So the theory says that square distance matrices are low rank, but our matrices are not square distance. We have the diagonal and all that. So then instead of we're using the theory for intuition, but we're going to then test and see if there's anything like that on the matrices that we do care about, right? So then we went on this matrix repository and we downloaded 100 matrices or 1,000 matrices, a lot of them. And we computed then the SVD of these distance matrices directly. Because for small enough matrices, we can actually compute the whole thing. We just leave it running overnight, and then we can see, okay, what do these look like? Then it turns out that, so what this plot is showing is essentially how many singular values of the whole Laplacian matrix I were to keep, right? So a fraction. So if I were here, essentially saying, look, pick half of them, or pick only 20% of them, pick only 10% of them, okay? And the vertical number is approximation loss. So the higher it is, the worse it is. So if we were to use directly the Laplacian matrix, which is the one with the big diagonals, right? Essentially, there's nothing we can do. We would lose, right? Anything we do that throws away a lot of data, we would lose essentially all of the energy there, right? And the reason for that is simple, right? We have like this big diagonal matrix that essentially is making this whole thing look like one identity matrix plus a little bit of noise, right? And since an identity matrix is pretty much as high rank as you can expect, this shouldn't work, right? But let's try to think a little bit different, and let's say, well, we know that the diagonal is kind of not interesting. It's just a sum of all that stuff, right? So let's just take the rest of it, right? So let's look at the SVD of the off-diagonal value matrices. And now things are a lot more interesting, right? So these are the largest. So the color map here goes from small matrices to large matrices. And I think these have 10,000 elements, okay? And now in this case, what would happen is, if I were to keep, say, 10% of the values, there isn't that much that I will lose more than, say, 40% of the energy, right? And you can see how the concentration of the all those points that were all the way up there, they were losing a lot of stuff, are pushed all the way down here, right? And the tendency seems to be that the larger your matrix get from that repository, which we're hoping models real-life matrices, the fewer elements you really need. So as the matrices get larger, it's not the case that you need more rank. It's the case that you need less rank, right? So then there's some hope that we're going to say, let's pick a constant number, and that will be good enough. Yeah, Jeff?
So if you looked at now what the fraction of the rank is, or what the total rank is?
The total rank for these is probably going to be...
It's still growing, right?
Yeah, so yes. So, and it's probably going to be pretty much the whole thing, right? So some of these matrices are full rank, right? But most of the singular values in the end are very low compared to the singular values of...
so I'm asking, if you want to only get, say, 20% error.
Mhm.
As the size of the matrix grows,
Ah.
that the rank you need still grows with that.
It's not clear to me. So this is why I was saying that this is essentially, we're picking here, so these points were, if we were to pick 100, okay, so this particular point here means that we're picking 100 singular values and we're dropping everything else. So if you were to pick 100 singular values for this matrix, this would be the loss. If we were to pick 100 of them, so this is a fixed amount, right? So it's actually reducing the percentage, right?
Yeah, yeah.
So you can see that it's actually, or some of them get bad, but in general it seems to be reducing.
Okay, okay.
And so this is my argument for the real life matrices, at least as they are sent to the repository, tend to be such that a constant number of columns is good enough for us to sample. And so that's what we're going to do. We're going to say, we're going to take all of our matrices. Actually, I should have an extra slide here. So let me go back to our formulation here. So we're going to take this guy here, and we're going to split it into the diagonal and the off-diagonal, and we're going to compute the SVD of that and only pick a few of them, okay? So that's the recipe, right? We're going to say, remember that this guy here has this boring diagonal, which we're going to throw away, and we're going to reconstruct after. We're going to compute the SVD of whatever's left, which we just have seen is enough to take a skinny amount of that, right? Okay, so why are we not done? Well, we're not done because what is the main problem with the SVD? That I actually have to have the matrix, right? If I don't have the matrix, how do I compute the SVD? And I just told you that the matrices that we have billions of elements in them. So how do we make this work? And it turns out that there's this miracle of a paper that came out 80 years ago that this is really miraculous, okay? This is amazing. So it says that if your matrices are of this kind, in which most of the singular values are small and only a few of them are large, you can actually get an approximation of the SVD by just sampling a few of the columns of the matrix randomly, scaling them so that the Frobenius norm of your approximation of your sample, it looks the same as this one, so it's just sort of estimating how much total norm there is, and there's ways of doing that, and then you just scale everything. You compute the SVD of this small guy, and the left singular vectors and the singular values actually match the first ones. And on a matrix that's 30,000 by 30,000, a block that's 100 by 30,000 is not even 1% of the data, right? It's something like really, really, really small, and that's all you need. You compute that, the SVD of that, which is fast now, right? It's a tiny matrix. You compute that and you get the SVD of the original one, only the first few ones. But that's fine, because all we're going to do is take the first few ones and throw them away anyway, right? So this is what we're going to do. Right? So this is the recipe. We're going to compute a low-rank version of that, and we're going to solve it. Okay? And now it's a slide I really needed to have on the other side. So as I was telling you, our Laplacian is going to be the diagonal elements and the off-diagonal elements, right? The interesting thing is that we know that there's a boring way to reconstruct the diagonal, so we don't need it. So we split it off. We approximate it with a low-rank version, which you already know how to do. And then we reconstruct this guy by just multiplying it with a constant element and turning it into a diagonal matrix, which is trivial. And then all we have to do is solve this guy here, right? So now we have smaller matrices here. This is a diagonal matrix, right? Remember, it's an SVD. This is one matrix, this is another matrix. This is another diagonal because it's this guy here. And all I have to do is solve this, right? Well, how do we do that, right? We don't want to multiply this out because if we multiply this out, it's big, right? Now, if you've done signal processing, you've probably heard of this thing called the matrix inversion lemma, which is this other crazy trick. That it turns out that if you have an expression that looks like that, and you search around for it, you're eventually going to find this. I spent a week trying to figure this out, and then I learned that it was supposed to be, I should have known that, and I didn't. There's that expression on the right-hand side there that says, this is exactly what it is. And the cool thing about this expression is that if you look at the inverses carefully, A is a diagonal, right? Remember, it's trivial to invert. Sigma is another diagonal. It's also trivial to invert. And this other inverse here, if you look at the dimensionality of it, it's actually a k by k and not an n by n, right? If the matrices that you have there are n by k by k, and so on, this guy here is much smaller. So that inverse you can actually compute. Right, so you can actually invert that guy there, or you can actually solve the linear system as you're pushing it through. But the point is, you can compute that whole inverse on the left there, that is an inverse of an n by n matrix, only doing n by k kind of computations if you have that structure. So that's exactly what we need, right? All we have to do is compute those guys there, and then solve the whole thing through. Aside from one snag, which is, remember, if you look back here, we constructed the diagonal matrix exactly so that this would hold, right? That's the definition of a Laplacian matrix, right? It's one for which if you send a constant vector in, you're going to get 0 out, right? So that means that our friend in the back there, right in the corner, it's not invertible. And so the matrices don't have inverses. And so all we need to do is we need the pseudo-inverse instead. So actually, if you just push it through, it doesn't work. So you need the pseudo-inverse. And so how do we get the pseudo-inverse? Well, first, what's the pseudo-inverse, right? If you've ever had to do like least squares fitting, right, in which you have to find sort of the closest thing, right, what turns out that you're doing is really using the pseudo-inverse of that, right? It's a matrix that holds these properties. It kind of, so if you have M, they call usually M plus or M cross, the pseudo-inverse of that. And the properties are that on the right-hand side, it kind of looks like the identity, right? So it's essentially an inverse for the column space of M. It's an inverse for the row space of M plus, and it's symmetric, right? So these things define the pseudo-inverse. And so it's kind of like the closest to an inverse you could get when the matrix is not invertible, right? And so now what we need to do is compute that. And then there's a little bit more of extra work in which we say, okay, now we know, because we constructed it, we know the span of that guy, right? So even though it's not invertible, we can kind of pretend that it is, because since we know the null space exactly, we constructed it to be that way. If this matrix is not invertible, adding this guy makes it invertible, right? That's the only thing that's in the null space. Okay, so we're just going to take that. We're going to write B as A plus this, right? And now we know this is invertible. Now we take our matrix inversion lemma friend and we just push it through and we can compute the inverse of that. But how do we solve that? Well, it turns out that B also works under the matrix inversion lemma, so we apply it again. And so we have sort of nested matrix inversion lemmas, right? So a subroutine here needs to solve B using the matrix inversion lemma, and it needs to solve this thing using the matrix inversion lemma again.
It's really rank 1 update.
Yeah, in this case it's the Sherman-Morrison identity or something like that, but it's the same idea, right? When one is the generalization of the order. So you're pretty much there. If you want to compute the pseudo-inverse, you take the guy, you add it, you invert it, which you know, and then you project it out, right? So now we can solve that, and we're pretty much done. The right-hand side, turns out you can solve a little bit differently, because if you look at the way that we constructed the weighting functions, then this is what they look like. And essentially, this means that the ith row of this expression is just the sum of all unit length vectors from I to j, right? So this expression is xi minus xj divided by its length. That's just the unit length direction vector of that, right? And the reason we can do this quickly is if I have a... I ran out of time to make that diagram, sorry, but this is easy. So if you put all your points in a quad tree, okay, so your current iteration may have some points that are sitting over here, and have some points that are sitting over there, right? And essentially what this expression is doing is saying, take this guy and compute the sum of all unit length vectors from one to all the others, right? So these guys kind of look like this, right? They're pretty much the same for all these guys here, right? And the reason for that is that the distance from this guy to the centroid of this is much greater than the distance from these guys to themselves, right? So you can use exactly the same trick that people do for galaxy dynamics and gravity dynamics, which is the Barnes-Cut expression. And so you can actually compute this sum in log n time instead of actually having to iterate over all of that. All you have to do is put them on a quad tree, right? And then now you're really done.
That's the basic idea behind multiple, by the way.
Yeah, so...
Same thing.
Same thing.
Great. Two other names. There's some fingers right in front of the monitor.
In front of the monitor. Oh, there you go. Thanks.
There's actually some wet ones there.
I think we're... So, that didn't look very good, huh?
Try this.
Thanks. So that's our algorithm, right? So we're really done, aside from all that algebra that is, in some sense, is necessary to make all the pieces come together. And it's kind of nice that there's, well-known ways of pushing all them through. But all of this really comes together from realizing that at the end of the day, you can do approximate SVDs. And that's sort of the takeaway lesson.
So there are other ways to do approximate SVDs. I mean, it all depends on how many singular values you need to keep. I mean, there's power series technique and other things.
There's which?
Power series techniques where you can just calculate one at a time, and if you only need a few of them.
You can do that if you actually have access to the matrix and the matrix is sparse, right? So all these iterative methods for doing approximate SVDs, right? So you're looking at shift invert and all of those, right? They're like Krylov subspace, right? All you do is you take your matrix and you multiply it. Well, we can't have that matrix, right? This is the weird part about this, is that at the end of the day, right, remember that this matrix here is really, really dense. Right. And it's got 10 billion elements. So we can't even compute all of that, right? We're only allowed to like pick a few rows of that, and now you go make do. So all of those would work if you have access to the whole matrix. And in fact, that's how we, to go back to the results now to see, you know, what are the impact, that's how we compute these guys. So now I'm actually going to talk about what happens if you use this algorithm. And the first thing to know is that this is actually an approximate SVD. It doesn't give you perfect results. Okay, so this is what our algorithm would look like if we were to take only 10 singular vectors, but they're exact. Okay, so this is a 2,000 vertex graph, complete binary tree, and we say do that whole thing, but only use the first 10 singular vectors, which we computed using shift invert. Okay, because we had the whole matrix, right, which is not the case for everything. But the interesting thing is that only with 10 vectors, you can actually see that the growth structure of the graph is captured perfectly, right? Here is the decomposition of the complete binary tree into the first one, the second one, and the third one, and it gets it pretty right within the first 10 singular vectors, right? So really, really, you don't, it's not perfect. So
what's the depth of the tree?
So if it's 2047 vertices, it's depth 10 or 11, right? One of the two. So you can count them.
You try k equals 11.
What?
You try k equals 11. K equals the depth
yes.
of the... Okay, good.
So, but the interesting thing is that this doesn't do a very, very good job, right? Like it has some sort of center, and like the edges are not that ugly, but they are not great. But the interesting thing is we can raise k, right? So if use k equals 20, now at least part of this got right? It's partitioned it halfway. So the approximate SVD is not giving us the perfect result, but as we get slightly larger elements, it's giving us better results. So this is k equals 40, this is k equals 80. And here now you can start to see, okay, actually it's capturing some of this stuff, and it's working fine. So there's some hope that with a sufficiently large k, we would get a decent graph drawing. It's not a perfect graph drawing, but even this one would work a lot better to see the global structure of the graph than it would something like the just physics-based drawer, which would look pretty much the same as all the other ones, right? Locally they look great, but it doesn't give you any idea of the total structure of the graph. Okay?
For a tree, the inherent dimensionality of a tree is only 2 dimensions.
No. Metric, no. There's hardness theorems about metric embedding of trees. Okay. So it's not that simple.
Okay.
I can draw it out, but it's not that straightforward.
Okay, so you don't, there is no, okay.
There is no good embedding of it.
Huh?
You need like log.
You need log.
So,
okay, good.
So this is just to see, so if your graph is reasonably well behaved, so this is some sort of road network graph, and this is the results with SFTP, which is the previous algorithm that was sort of, it scales well. Our result is sort of similar, okay? So you can see that, so it bends somewhat more here, and in essence what's happening is that it's actually taking the influence of these guys much more strongly towards that than this previous one, which is just sort of quadratic. But sort of, if you were to say, okay, if I were to give you 2 pairs of vertices and ask you, are these close or are they far, both of these guys do a decent job at it. And ours is now explicitly saying, let's do a metric embedding, okay? I'm not ready to claim that each one is better than the other, or even that this one is better than the previous one, right? The point is that we're trying to now take a real metric embedding thing and see how it works, and in particular for large graphs, right? For a small graph like this, perhaps what you should do is use the exact one instead of the approximate one. And you could, but this is really just to show you that even for this case, it's not doing something entirely stupid, right? That you could go in here and examine the relationship between these guys and see what it got wrong and things like that. All right, so the point is to give you sort of a gross understanding of the whole thing, right? So this is a much larger graph, and this is one that a few of the different, so let me just show you a few. So this method is, the notable feature of it is that it's extremely fast. Okay, so this method will work on billion node graphs easily, but it doesn't do a particularly great job, right? I don't think there's very good. This is another one that works extremely fast. So this looks like MDS, traditional MDS and not metric MDS, and this is what it does for graph drawing. This is the result for SFTP, and I actually claim that this is actually okay, right? So it does find a few of these things, right? A few of these islands in here, right? So it's sort of saying, look, these guys are well connected to each other, but they're sort of far away from everything else. But it turns out that 85% of the vertices are in here, okay? So if you've never heard of the term hairball, this is it. Okay, so all these edges are sort of running over each other through the center here. Okay, and this is the local minimum of the force embedder. All right? And now this is what we get, which let me first start saying that I don't think this is the ideal result, right? This is not particularly great, and there's some strange radial artifacts happening either because of the embedding or because of our approximation. We're not quite sure. However, the interesting thing about it is that even as you're going way down the center here, you're still seeing these beams of vertices in which you're saying, look, there's a big cluster of guys here that all connect to each other in this way. So there's some relationship between what happens with this thing and what happens with these things. And if you look and pick some vertices here, they tend to be central. So you can sort of look at the average distance to all the other ones, and it reproduces these better than what happens in here. Okay, I'm not ready to claim that this is a great result, don't get me wrong. But I think we're doing a much better job at trying to elucidate the growth structure. And it tells me that there's something in here, and sort of thinking of it as a metric embedding problem might have a better result, right? So I guess part of the lesson here is that if you've never seen big graph drawings, like this is sort of the best you can get right now, right? And people would say, they would look at this and say, you know, a hairball drawing is impossible, right? Graph drawing, you shouldn't draw large graphs, you have to cluster, you have to do all these sorts of things. And really what they're talking about is the current methods for graph drawing generate hairballs, and we perfectly agree. And all we're trying to do is let's beat the current thing, and we believe we beat it. Right? We believe this is slightly better than the other ones. We believe it's trying to show the global structure. It's perfect? No, it's not, but it's doing a little bit of a better job in our opinion. So why do we think this is interesting? Well, this is really the first explicit distance embedding graph drawer that beats the cubic time and quadratic space. Okay? So if you pick k, in our case k is constant, we keep it 100 at every single experiment that you've seen. You need nk space, you need nk squared preprocessing time, and nk per iteration. Okay? So there is a limit which the people who have run user studies seem to say that the weighting matrix has a big difference in the resulting quality of our layout, and the one that we pick is not the one that they consider ideal. We need to pick that one in order to make this part work. If the distance is not just the inverse power of that, this doesn't hold. There's an extra dij term here that really wreaks havoc with like everything you try to approximate. So it only really works with the subcode. So that's sort of like the final piece that everything needs to come together. And so it's really an open problem how to do this sort of approximation when you have an actual arbitrary term sitting here. And this is what we would need for a better drawing. And in particular, some of the weirdness that we see here, we also see in the graph drawing papers that actually do this evaluation of using the different terms. And maybe then what we need to do is figure out how to make it work with a more general weighting term. But we're not there yet, right?
How many points
this is about 600,000, I believe. So the whole matrix is something like 200 gigabytes if we were to compute it. So, yeah.
I'm curious what the other weighting parameter looks like.
What
the other weighting parameter that is suggested to you?
It's square distance. So it's square of the graph drawing distance.
Okay, and what you're using?
It's 1 over dij. Yeah, so if I go back
to the square of that instead.
Yeah, it should be the square of that instead. And there is actually sort of a bit of a algebraic reason for that. So the term that we're using is dij to the negative 1. Yeah. So it's just dividing by dij. What people recommend using is dij to the negative 2 power. And if you look at why this is, it means that you get to push the weight inside here. This cancels out. And this becomes, then you're trying to make sure that the ratio of these guys approximates 1. By divide by dij, this becomes 1. Then this becomes xij over dij. And then what you're trying to do is not match the distances between them, but actually match the ratio to make the ratio go to 1. And so that's kind of the heuristic reason people say that you should use dij squared. Yeah. But we can't in this case because then none of our approximation works. So.
Okay. If I understand exactly how you're saying you need to use it, I think you might be able to push it through. But
maybe. I would love to hear it.
Okay.
If you don't mind meeting afterwards, I actually want to hear that because this is sort of, we had to settle for the non-optimal version of that. So, but that's pretty much it. And other thing that's interesting is that really we're using this for drawing graphs, but in a sense we didn't have to, right? This is fundamentally just doing metric MDS, if you've heard of this. in an approximate sense. And so perhaps what we can do now is just use this for pure dimensionality reduction, right? There's problems in which you don't have access to the whole distance matrix of this thing, and you want to literally just embed it into RD, right? So perhaps we can do something like that. Again, the main problem is that there's a hidden exponential dependency on D here, right? That Barnes-Hut scheme blows up exponentially as you increase that, right? So if you were to do this in R to the 10 instead of R squared, then maybe that thing there needs to be using like locality sensitive hashing and all these really fancy metric techniques, right? But we haven't looked at any of that. We just figured this is sort of like the way we have to go. So.
And that's exactly my question, is why do you settle for D equals 2? I mean, because
you can't draw anything with D equals 5.
No, D equals 3 or 4, you can draw it and then project it, because, then rotate it and project it, because that might
That's what he's doing already.
That's what he's implicitly doing.
He's already projecting to 2 dimensions.
Yeah, no, but
instead of going to 3 and projecting again, you're doing it.
You could do it interactively. So
yeah,
you could do it interactively, and maybe there's something there.
It makes sense, right? Because you can visualize something.
Yeah.
Right.
Well, you can use Grand Tour, and there's all sorts of stats graphics guys that like you do RD and then you do like random frames in 2D and you keep looking at them and stuff. But the traditional setup is R equals 2 for all the other graph drawing stuff. So we decided, let's compare to what like other people have done instead of. But you're right, we could do R3, R4. I think anything much larger than that, you're just going to run into terrible partitioning things, right? Like your log n is just going to degenerate into a linear search.
But the other thing that's interesting though is then look at what is the intrinsic dimensionality of your graph as your error changes with D, and then you know how well you can possibly do.
Yeah.
Because look,
I think there's
graphs that are going to be simple graphs that are going to just look terrible no matter what.
Yeah, and then you can start thinking about doing clustering and doing graph parsing until your dimensionality is low, and then at least you have some statement to say this is the reason I want to do clustering of the graph before I draw it. So yeah, you can do all sorts of interesting things with this. It's just that like before we actually need to write all of those, we need to first get the basic technique working. So that's.
I was sort of wondering, I think it might be along those lines, is if there's sort of methods that you could use. I mean, since your approach, you sort of claim that you can capture the scalable structure better than a lot of other methods. Is there a way to use the results you get sort of in a bootstrapping method, sort of an initial input to some sort of other way of laying out a graph?
Yeah, so there's a lot of sensitivity to initial guesses in a lot of these dimensional. So one thing we should have done is perhaps claim that maybe the problem with the previous algorithm with this is that it gets a bad initial guess. So one thing we could have done is take our algorithm, give this guess, and then try to use this as initial guess for something that might have quadratic behavior, but you only run it for 1 iteration or 2 iterations and see where it goes. So there's a lot of like tricky engineering interplay between these things, right? So if you look at the actual software that the guys in my research group release, like the papers say, here's how you do it, and then you look at the software and there's like 20 different little steps that they have to do in the way to actually get the graph to look right. So I don't doubt that this could be used as, say, an initial guess for something else, or something else needs to come up before this to actually make it work in practice, right? So I can definitely believe that this wouldn't work sort of straight out of the box. But the goal here was try to show, look, there's interesting low dimensionality phenomena happening. So, yeah.
I may have missed the answer to my question, but is there any particular reason that you need to compute the pseudo-inverse directly, and not just use it as a half of like a left divide or something like that?
So to be honest, that's my least favorite part of this. Like this was the only way we found to push this through was to add that stupid extra piece of the null space and then project it out. Just that I don't know any other way to find the inverse of this, because we can't compute that inverse directly through the matrix inversion lemma because it actually has a kernel, right? It actually has this, so that inverse doesn't exist, right? There's more than one, right? So there's many different solutions for this, and then the matrix inversion lemma just sort of doesn't apply, right? Like you actually don't get the right thing.
Well, I guess my real question is why not to compute a lower rank version of the matrix and then use it in a linear solver?
Because I don't know how to do that. Maybe there is a simple way to doing this, and I am certainly willing to believe that there might turn out to be something much simpler to do that works and doesn't require this 2-step matrix inversion thing.
Okay.
but I just don't know how to actually make the details work without, you know, computing the whole dense matrix and then doing something like that. And so maybe we are missing something very, very basic here, but this was the way we found to sort of make the whole thing work.
Maybe I'll talk to you after.
Yeah, I would love to just replace all this with something simpler. So I just don't know how to do it right now. Yeah.
Can you use some kind of clustering or hierarchical methods to just speed up the?
Yes. There's you could take this is how this method really works, right? So you do a multipole thing, but you actually do it in. So there's two levels of the hierarchy. You solve that Barnes-Hut scheme, but you first find the initial solution for a coarsened version of it. Then you split the clusters, do it again, and split the clusters until it converges. So yeah, we should do that. We haven't because most of the other stress majorization algorithms don't do it, and we wanted to keep the comparisons in some sense in the same level. But again, this is one of the questions that probably when you want to get like a really solid, robust implementation, you want to do like a high-level coarsening of this, and then do within the clusters and all that. But then you have to start worrying, picking different clusters, will it affect this or not? So like there's other questions that we wanted to see how much the pure thing would get us through, but perhaps we need something like that for later for actually get like timing it just right. So yeah, there's like a whole field of graph clustering that we sort of know we could use, but we haven't. I can talk to you later. Just yeah.
Just a quick question about the approximate SVD. So in practice, do you actually just randomly sample the rows? Like
no. Okay. So
how do you actually do it?
so our let me just find the expression here, right? So what we're trying to find is a matrix where there's zeros here, and these terms are the ones that we're trying to approximate. And these are the inverse distances, right? And so we could sample them randomly, but it turns out that each row of this is one run of the Dijkstra algorithm, right? Because you get from single source shortest paths. And then what we found in practice works better is that you run one of these and you keep a running tally of the furthest out vertex that you haven't actually sampled yet. You pick that guy, run Dijkstra again, update the rule, and run Dijkstra again. And so you sort of get like a well-distanced seed of points for which you're going to compute. Which the theory doesn't say anything about how good it should approximate, but turns out we beat it by about 10% of the approximation loss in practice. But we can't prove anything about it. So, but yes, you're right. It's not just sample it uniformly. The theorems do hold in that case, but the bounds are a little loose, and so there's yeah.
Well, there's certain things you can say about sampling things in that way.
I'm sure someone who actually knows some theory can make this work. I don't, right? I read the paper and it's like, algorithm, that's what I want. So
you're using some form of random sampling still?
The first one is random.
What?
The first vertex that we pick is random.
Okay, but everything else with that is...
Everything else is deterministic. And we actually ran experiments where we compared the approximation loss with this scheme versus uniform sampling versus actually computing the sample. So the true sampling that they ask for actually requires reading over the whole matrix at least once. So it's 2 passes. So the first you compute the square lengths of the rows and then you sample proportionally to the square lengths.
Right.
But we can't do that in our case because that would require computing all pairs shortest paths on a dense graph. And that's again, right, would be sort of like a really long and So then our method had the advantage that we didn't even have to look at those elements, and we're exploiting kind of like the metric structure of the graph for that. But again, it's another lucky break, right? If we didn't have that, it wouldn't work, and so.
I guess many of the weights these metrics in L are close to 0. Far away.
Less than you would expect, right? So for some matrices, you're absolutely right. This is what happens for some graphs, right? So for graphs that tend to be high diameter, this happens. But this is, again, one of those things that if I had more time, I would have put it in the talk. But for the matrices or the graphs for which this phenomenon happens, in which you have these really long distance critical paths, are ones for which SFTP tends to work well, because you have a sequence of edges that are saying this guy should be far from this guy should be far from this, and so like this sequence of edges tends to straighten itself out nicely, right? So the graphs for which we want to draw things and SFTP does not do a good job are the small world graphs, if you like that term, which are things like World Wide Web crawl, right? In which the diameter in here is pretty low. The diameter is something like 8 or 9, even though there's 500,000 vertices, right? So the shortest path metric is not, so 1 over 9 is really not that close to 0, right? And that's the smallest value on the matrix, aside from the diagonal, right? So you can't just, we looked at sparsification, which is, you just pick some threshold, set it to 0 and invert it. It doesn't work as well as this. And the other problem is it still requires you to actually compute all the distances before you decide which ones go to 0, right? And computing all that is all pair shortest paths. And that's, n squared log n or something like that. And that's n squared time when you have 100,000 vertices. Maybe you can do it in a cluster, but it's not very good, right? So you can do something like that, but beating the one pass over the whole data is that we couldn't make it work. Maybe there's a clever way that does, but we couldn't.
Because people are doing it mostly in the sensor network localization programs, where you have large networks of sensors and you want to find the locations of the sensor. You impose sparsity with the machine.
I would love to so I don't know the literature. I would love to know more details, and maybe something like that would work in our scenario.
You get about 5 to 10% sparsity. Then you can do the SVD on sparsity.
Yeah, the sparse SVD works great. No, I would love to point out that we can talk offline, because maybe there's a better way of doing this.
So can you tell us why AT&T, what is their interest in looking at graphs? No, seriously.
No. This is a great problem. So AT&T has a pretty large network, right? So not only a cell phone network, right, but they hold a lot of backbone, right? So one of the things they care about is the autonomous systems backbone of the internet, right, which is not that large of a graph by today's standards. But by 10 years ago, they were huge, right? It was something like 60,000 systems talking to each other on a graph, and you want to look at things about this graph. And yeah, you can write algorithms that'll try to analyze it, but really, right, sort of, Tukey worked in the Bell Labs, right? And like the mantra is, before all else, draw a picture, right? Like this is their exploratory data analysis thing, right? So people do take that to heart there, right? Which is nice. And how do you draw a picture of 60,000 vertices? Nowadays, you can do something like straight stress modularization. Back then was a really hard problem, right? Nowadays, the problem is not perhaps how to draw the network of the autonomous systems, but how to figure out how to draw the network of cell phone clients, for example, right? Like you want to get these big pattern. So we actually haven't drawn it, but this is sort of the natural problem that you think about, right? I don't have so I think the first plot was this. I'll say it quietly so that the lawyers don't hear me. But this is our art chart, right? Just plotting this, right? This is 500,000 people, okay? It's not that you can't really get a lot of interesting stuff by putting in an Excel table and trying to read through, right? It doesn't work, we know that, right? But what does work then? Drawing a graph turns out works pretty well. We've actually seen things that were interesting by sort of drawing the graph and putting the right attributes on top of that, right? So they're a nice way of modeling problems, and we have lots of large graphs inside. So that's one of the reasons they care about graphs. But there's other problems that the people care about too, right? So a lot of the stuff we do is graph drawing, but there's a lot of things that they do, which is just embedding in low-dimensional spaces. So they were looking at things like clustering usage patterns using sort of Earth mover distances and dimensionality reduction, which was published at KDD a while back. Some collaborators of mine were working on that sort of stuff. So, and it turns out that you can, a lot of the stuff that goes into information visualization when you extract the algorithms looks like a lot of the stuff that data mining people do. And so there's like a lot of interesting interplay that's going on there. And so we sit probably in sort of a strange space in like InfoVis groups, which is a lot more sort of algorithms, and then we always get our reviews. They all hate that we don't really know much about our users, and that's very true. We don't, but we're trying to look at it from a slightly different perspective. So that's sort of our story. So,
all right, well,
and we're hiring.
all right, with that, we'll